Imagine waking up on a Monday morning and your entire global enterprise is suddenly just dark.
Like a total blackout.
Exactly, but not because of a localized power grid failure or anything like that. It's because the invisible, edge-to-edge pathways that connect your cloud servers, your branch offices, your whole supply chain, they've completely bottlenecked.
Just completely jammed up.
Right. In an instant, million-dollar transactions halt, customer trust just evaporates. Your entire workforce is basically paralyzed.
It's terrifying.
It really is. You're staring at logistics dashboards that have simply flatlined.
Yeah.
You've got trucks sitting idle at loading docks because, well, they can't access digital manifests, and your customer service lines are completely dead.
Oh, wow. Yeah, that is the ultimate nightmare for corporate managers.
It is the ultimate nightmare. And, what's truly terrifying is that for a lot of organizations out there, the legacy telecommunications infrastructure they rely on every single day it's a shocking vulnerability hiding in plain sight.
Just waiting to buckle.
Just waiting to buckle under the demands of modern high-speed corporate operations.
Well, to ensure you always maintain a competitive edge in the hyper-connected marketplace and to guarantee you never have to live through that specific Monday morning nightmare, take a moment to like, subscribe, and share this deep dive.
Definitely.
We also explicitly direct you to the description below. We've got access to additional corporate resources, network diagrams, and some really essential technical reading that will help you map out and secure your own infrastructure.
Welcome, everyone. You are listening to Chapter 11, Wide Area Networks, out of our comprehensive 15-chapter arc.
Glad to be here.
So in our last installment, that was Chapter 10, Wireless Networks, we explored how the IEEE 802.11 family of standards and, robust WLAN security designs really liberate the mobile workforce.
Right, getting people off the literal wires.
Exactly. We established that securing the local airwaves is critical for edge productivity. But today, we are zooming out. Way, way out. We are mapping the macroscopic pathways. Today, we're analyzing the business drivers, the technologies, and the strategic solutions that power modern wide area networks, or WANs as we call them, for every scale of business.
It's a huge shift in scale.
It really is. We're moving from the local office into this vast, interconnected web that links continents, cloud providers, and remote data centers.
The wide area network is effectively the circulatory system of the modern enterprise.
That's a great way to put it.
Yeah, but to truly govern it, you can't just look at the technology itself. You really need to understand the underlying business drivers pushing its evolution.
Okay, so what are those drivers?
Well, when we evaluate WAN business drivers, we are primarily looking at 4 key strategic needs. First, connecting multiple geographic locations seamlessly.
Right, because nobody works in just one building anymore.
Exactly. Second is enabling rapid, secure cloud migration. Third, ensuring high network agility. And fourth, and this is a big one, achieving deep network visibility.
Visibility is huge.
It is. Every technological choice an enterprise makes regarding its WAN really must serve at least one, if not all, of those core drivers.
Okay, let's unpack this because, well, that sounds great in a boardroom, right?
Oh, totally. Very corporate.
Yeah, but in practice, why do corporate managers actually need to understand the historical evolution of these networks? I mean, if the goal is just to connect point A to point B, why shouldn't a modern executive just turn to their IT procurement team, say, go buy the newest, fastest tech on the market and wash their hands of it?
Right, the old just throw money at it approach.
Exactly. Why doesn't that work?
Because treating enterprise networking like buying a new smartphone is a trap. It just destroys IT budgets.
Really?
How so?
Well, you cannot simply buy the newest technology without understanding the environment you're integrating it into. The reason executives must understand the evolution of WANs comes down to a critical concept known as legacy debt.
Legacy debt, as in old technology we're still paying for. Exactly. Your enterprise, or, the partners you do business with, they likely still rely on older infrastructure embedded really deep within their operations.
So like a hidden anchor.
It's totally an anchor. Understanding this legacy debt is absolutely vital for financial and operational forecasting. You just cannot accurately predict your IT budget or guarantee your network's scalability if you don't realize you are paying exorbitant monthly fees for, say, a 30-year-old circuit switched line.
And that old line is probably quietly acting as a choke point for your brand new state-of-the-art cloud application, right?
Precisely. You're putting a Ferrari engine in a horse-drawn carriage.
I see. So you can't chart a course for a high-speed future if your anchor is still dragging on the bottom of the ocean.
Right.
So let's trace that lineage so we know what that anchor actually looks like. Let's go all the way back to the 1970s.
The early days.
The era of the analog modem. And, for those of us who remember the screeching sound of a dial-up connection, it is wild to think this was once the bleeding edge of corporate telecommunications.
It really was revolutionary at the time, though, because it solved the massive physical problem.
Which was?
Well, computers speak in digital, right?
Yeah.
Discrete ones and zeros. But the only global communication network that existed in the 1970s was the telephone system.
Which was built for human voices.
Exactly. It was built to transmit the continuous analog sound waves of the human voice over copper wires. So the word modem is actually a portmanteau of modulation and demodulation.
Meaning it translates between the two formats?
Precisely. It was this clever technique for taking the digital ones and zeros of a computer, modulating them into analog audio tones that could travel over those standard copper telephone lines, and then on the other end, demodulating them back into digital data.
That's where that awful screeching sound came from.
Yeah, that was literal data you were hearing. But the physical limitations of pushing data through analog voice channels meant transmission speeds peaked at just 56 kilobits per second.
Wow, 56K.
Yeah. To give you some modern business context, downloading a single high-resolution marketing graphic at 56 kbps would take several minutes.
Just for one picture.
Just one.
And obviously, a large corporation couldn't just keep, dialing in every time they needed to send a file. If you needed a constant connection between, say, a bank headquarters and a local branch, how did they handle that back then?
Right. Dial-up wouldn't work for that.
That's right.
So they used analog leased lines.
Right.
This provided an always-on point-to-point transmission path.
So they basically rented a wire.
Literally.
Yeah.
A business would pay the telephone company to lease a dedicated copper wire that physically connected their headquarters to that branch office.
That sounds secure. And
Oh, it was highly reliable because it was dedicated entirely to that business.
Yeah.
Nobody else could use that specific copper path.
Yeah.
But it was incredibly expensive.
Right, because you're monopolizing a physical asset. And as we moved into the 1980s, the technology shifted to digital, but that fundamental architectural problem, the dedicated line, that remained, didn't it?
It did. The 1980s introduced circuit switch digital networks. We saw the rise of the public switch telephone network, or PSTN, being upgraded with digital switches.
Okay, so a bit of an upgrade.
Yeah, and the introduction of ISDN, the Integrated Services Digital Network.
Yeah.
Service providers started replacing those old analog transmission switches with digital ones.
So data didn't have to be translated into sound anymore.
Right. We started seeing the DS-Aero, DS1, and DS3 families of digital communications. But fundamentally, despite being digital, these were still circuit-switched networks.
Let's use an analogy here to make the mechanism of circuit switching concrete for the executives listening. Think of circuit switching like a dedicated private train track built between two cities just for one specific train.
I like that.
Yeah, so if your company in New York needs to communicate with your branch in Chicago, the circuit switch network literally builds a dedicated physical or virtual track between them for the exact duration of that communication.
And then that track cannot be used by anyone else while your circuit is open.
Exactly. It is highly reliable. There's no traffic on your track.
None at all.
But think about the business cost there. It is incredibly inefficient and financially disastrous if your train isn't constantly running back and forth.
Which it almost never is in a corporate environment. Data is bursty.
Right. If you are only sending data for 10 minutes every hour, you are still paying the telecom provider for that track to sit completely empty for the other 50 minutes.
Which really highlights the sheer financial inefficiency of legacy telecommunications. In a circuit-switched environment, you're paying for the total capacity of the circuit 247, regardless of your actual utilization.
That's wild.
It's a massive capital expenditure drain that modern businesses simply cannot afford.
So if circuit switching was this expensive, inflexible standard, what happened in the 1990s? I know satellite communications started becoming a major player for corporate networks around that time. Did that solve the track problem?
Well, satellite communications became highly relevant because they bypassed the need for physical tracks altogether.
You just beam it up.
Exactly. They could provide the equivalent of a leased line to anywhere on the planet without needing to run physical copper or fiber cables across oceans or mountains.
Which is huge for certain industries.
Absolutely revolutionary for connecting highly remote sites.
Mm-hmm.
Think offshore oil rigs, maritime logistics vessels, or really refining operations.
But there is a massive caveat there, right? I mean, I
Yeah.
hear executives sometimes asked, hey, why don't we just use satellite for everything if it's wireless and global?
Oh, yeah. The caveat is the physics of latency. While satellite mimics a leased line, it is primarily utilized today as a disaster recovery solution for backup bandwidth. It is emphatically not ideal for real-time applications or time-sensitive protocols.
Walk us through the mechanism there. Why exactly does satellite struggle with real-time apps?
It's pure physics. A geostationary satellite sits about 22,000 miles above the Earth.
That is a long way.
It is. So when you send a data packet, it has to travel 22,000 miles up to the satellite, be processed, and then travel 22,000 miles back down to the receiving dish.
Right.
That 44,000-mile round trip inherently introduces a delay, usually around 500 to 700 milliseconds.
Now, half a second doesn't sound like much to a person on the street.
No, and for sending an email or downloading a static file, that half-second delay doesn't matter at all. But for real-time applications like a VoIP phone call, remote video conferencing, or high-frequency automated trading,
Oh, it's brutal.
it renders the connection nearly unusable. In a VoIP call with a 700 millisecond delay, people end up talking over one another, the conversation loses its natural rhythm, and automated applications will simply time out, assuming the connection has failed.
So the actionable takeaway here for IT leaders and corporate managers listening is this. You need to immediately assess your current infrastructure for hidden, costly legacy circuits.
Look at your telecom bills.
Yes, look at the bills. Are you paying for dedicated ISDN lines, old lease circuits, or primary satellite connections that offer poor bandwidth to cost ratios? If your business operations have evolved into the modern era, but your telecom contracts haven't, you are just bleeding capital.
Exactly. The evolution from those rigid circuit switch networks in the 1980s to packet switch networks in the 2000s completely rewrote the financial and operational playbook for enterprise architecture.
So we stopped building dedicated private train tracks.
Right, and we started using shared highways.
Okay, so we have this massive shift. Enter the 2000s, the backbone revolution. This is where we see the rise of SONET.
Yes, huge development.
But before we get into the acronym, what physically changed in the ground? What were they actually laying down?
We moved from copper to glass.
Fiber optics.
Exactly. SONET stands for Synchronous Optical Network. This was an absolute game changer. It was developed primarily as a standardized method for service providers to deploy high-speed optical fiber backbone networks.
So shooting light instead of electricity.
Right. Instead of sending electrical impulses over heavy copper wires, we are now using lasers to transmit pulses of light through incredibly thin strands of glass.
And crucial to its design, SONET was deployed by service providers in a ring topology, rather than just straight lines, right? Why is a ring so important for business continuity?
Let's look at the mechanism. A SONET ring physically loops around a geographic area, say a major metropolitan city like Dallas or New York. It uses two counter-rotating rings of optical fiber.
Counter-rotating, so data travels clockwise on one ring.
And counterclockwise on the other.
Okay, so if a construction crew with a backhoe accidentally digs up the street and severs the fiber optic cable on the east side of the city.
Which happens all the time, by the way.
Right. What happens to the network?
The SONET hardware detects the break in milliseconds. And because light travels at 186,000 miles per second, the system simply bounces the traffic back the other way, sending it the long way around the west side of the intact ring.
Oh, wow. So it just instantly reverses direction.
Exactly. This results in a failover time of less than 50 milliseconds. The end user never even notices a disruption.
That's incredible.
It provided unprecedented redundancy and resiliency at speeds that were previously unimaginable, and that formed the core backbone of the modern internet and enterprise WANs.
Okay, here is where it gets really interesting for an enterprise. Once that massive, resilient optical backbone was in place, the way we routed data through it fundamentally changed.
We finally ditched the circuits.
Right. We moved away from the circuit-switched model to packet switching, and specifically to MPLS.
Multi-protocol label switching.
Well, yes. How exactly did MPLS revolutionize the packetized backbone?
MPLS is a brilliant piece of engineering. And while the mechanics are highly technical, the strategic implications for management are profound.
Okay, break it down for us.
To understand why MPLS was necessary, you have to understand why traditional IP routing at layer 3 of the OSI model is so slow.
When you say layer 3, for our non-engineers listening, we're talking about the network layer where traditional IP addresses live, right?
Exactly. Think of a traditional layer 3 router like a very thorough but very slow post office worker.
Okay, I like this analogy.
a data packet arrives. The router has to open up the digital envelope, read the full destination IP address, and then consult a massive routing table, which is basically like a giant phone book.
Right, looking up every possible route.
Yeah, to figure out the absolute best next stop on the journey. Then it repacks it and sends it on. Doing that millions of times a second requires massive computational power, and crucially, it creates latency.
Right, if every single post office worker on the route has to stop, read the full address, and check a map, the mail slows down significantly.
Precisely. What MPLS does is bypass that heavy Layer 3 lookup process entirely. MPLS is a packet switching technology that operates at Layer 2.
The data link layer.
Right. When a packet enters an MPLS network from your corporate office, the very first router, the ingress router, slaps a short, simple label on it.
Like putting a barcode on that envelope.
Exactly like a barcode.
Yeah.
From then on, every subsequent router in the core network doesn't bother looking at the complex IP address.
It doesn't check the map.
It doesn't check the massive routing table at all. It just scans the simple barcode label and instantly forwards it to the predetermined next hop. The label tells it exactly where to go. It is exponentially faster.
And structurally, it allows IP traffic to flow in full or partial mesh configurations, meaning there are multiple redundant paths the data can take if one node goes down.
Yes. And for the corporate application, this is why MPLS became the absolute gold standard for the enterprise WAN for nearly 2 decades.
Because of the speed and reliability.
Because it is so fast, so predictable, and so reliable, it is ideal for voice over IP, streaming, and time-sensitive applications. Service providers aggressively adopted MPLS switches because it finally allowed them to offer guaranteed performance metrics.
Like strict service level agreements.
Exactly. Strict SLAs over a shared packet switch network.
Okay, I'm going to push back here.
Go for it.
I want to play devil's advocate for a moment because this is an argument IT directors hear from CFOs all the time. Bandwidth is incredibly cheap today.
Very true.
I can go buy a 10 gigabit commodity fiber line for a fraction of what a dedicated MPLS circuit costs. So if my fiber optic pipe is practically the size of the Lincoln Tunnel, why do I need to authorize spending on complex MPLS networks and traffic prioritization? If the pipe is massive, won't all the data just get there instantly anyway?
It's a fair question, and it's a very common executive misconception. But throwing bandwidth at a network problem is a terrible financial strategy because it fundamentally misunderstands how data actually moves.
How so?
It's like trying to solve rush hour traffic by just building a 50-lane highway. Eventually, it will still fill up, and it costs a fortune in capital expenditure. But more importantly, in a corporate network, not all data is created equal.
What do you mean? A megabyte is a megabyte, isn't it?
In size, yes. In business value, absolutely not.
Okay, give me an example.
Let's look at a real-world scenario. Imagine your CEO is on a critical VoIP call, attempting to close a multi-million-dollar acquisition with a partner in Tokyo.
High stakes.
Very high stakes. Now, VoIP packets are tiny, but they are incredibly sensitive to jitter, which is the variation in packet arrival time.
Right. If they arrive out of order, the voice sounds garbled.
Exactly. Now, at the exact same millisecond, your IT department's automated system initiates a backup of 2 terabytes of server data across that same 10 gigabit WAN connection.
Oh, boy. Even on a 10 gigabit line, that database sync is going to flood the pipe, right? It creates a microburst of traffic.
It does. It creates a microburst that instantly fills the router's buffers. For a fraction of a second, maybe just 200 milliseconds, the pipe is completely choked.
And what happens then?
Well, for the database backup, a 200 millisecond delay means absolutely nothing. It just keeps copying. But for the CEO's VoIP call,
those voice packets get stuck behind the database packets.
Yep.
The CEO's voice becomes robotic, packets drop, the audio warbles, and the call might just disconnect.
Precisely. You just risked a multi-million-dollar deal because you treated a database backup with the same priority as the CEO's live voice.
That is a brilliant example.
That is why managers must authorize spending on traffic prioritization. We manage this through quality of service, or QoS, and class of service, or CoS. They are different mechanisms, but they serve the same critical business goal.
Let's break those down. How do they actually work under the hood?
Well, QoS operates at Layer 3. It utilizes something called the type of service, or diffserv, bits within the IPv4 packet header.
Again, let's translate that for the executives. The packet header is basically the shipping label on the digital box. So what are the diffserv bits?
Think of diffserv as a bright red, neon, urgent VIP sticker placed directly on that shipping label.
Okay, that makes sense.
It literally tells every router along the path, this specific packet is high-priority voice traffic, put at the absolute front of the line ahead of everything else. It allows you to guarantee fixed bandwidth for critical applications.
And how does that differ from class of service or CoS?
Networks that support both Layer 2 and Layer 3 networking can benefit from CoS at Layer 2 and QoS at Layer 3 to really make sure time-sensitive IP packets are transmitted to the destination first.
So CoS is just at a different layer.
Right. CoS acts as an identifier in IUAE 2.1p Layer 2 frames. It's a slightly different technical application, applying the priority at the data link layer rather than the network layer, but the strategic outcome is identical.
Ensuring that time-sensitive data jumps the queue ahead of bulk non-sensitive data.
Exactly.
So the actionable takeaway here is non-negotiable for enterprise leadership. Managers must prioritize traffic shaping.
It's mandatory.
A CEO's VoIP call, a surgeon's remote telemedicine video feed, or a financial institution's high-frequency trading data must jump the queue ahead of a background database backup or an employee downloading a training video. Understanding QoS is how you ensure that your network aligns with your business priorities, rather than just letting all the data fight it out in a massive pipe.
This raises an important question, though. Traditional MPLS networks are incredibly reliable, and they beautifully support QoS. But they have a fatal flaw in the modern era of hyperagility.
What's the flaw?
They are highly dependent on proprietary hardware, they are inherently static in nature, and they require physical connections that are hardwired by the telecom provider.
Right, let's look at the business friction there. If your company acquires a new subsidiary and you need to open a branch office in a different state, connecting it to your existing MPLS WAN is a nightmare.
It takes forever.
You have to call your telecom provider, sign a new multi-year contract, wait 60 to 90 days for them to physically trench the fiber lines to the building, install their proprietary routers, and manually configure the bandwidth optimization line by line.
It is a slow, manual, time-consuming process.
Which brings us to the paradigm shift of the 2010s. The transition from static networks to dynamic orchestration. We're talking about SD-WAN.
Yes. Software-defined WAN, or SD-WAN, is arguably the most significant revolution in enterprise networking of the last decade.
That's a big statement.
It's true. It fundamentally decouples the networking hardware from its control mechanism. In a traditional WAN setup, the control plane, the brain, that calculates the routing tables and decides where traffic goes, is locked inside every individual physical router.
So you have 50 routers, you have 50 brains.
Exactly. In SD-WAN, we extract that brain and centralize it in software.
Okay, let's unpack this architecture. Because the first time I heard about SD-WAN, it sounded like magic, but it's really just brilliant abstraction. SD-WAN builds and configures virtual connections, creating what we call overlay tunnels across various underlying physical links.
Right, it sits on top.
It actually doesn't care if the physical link is an expensive MPLS circuit, a cheap commodity broadband connection, or even a 5G LTE cellular signal. It treats them all as a giant, agnostic pool of available pathways.
Precisely. Let's break down the three core components of this architecture to understand how it works. First, you have the SD-WAN controller.
The central brain.
Yes, this is the centralized software brain that makes all network traffic flow decisions. It has a holistic, bird's-eye view of every single link, node, and connection in the entire global network.
But hold on, if we centralize the entire brain into a single software controller, haven't we just created a massive single point of failure? If that controller goes offline, doesn't my entire global network go completely blind and shut down?
That is exactly what an auditor would ask, and it's a great point. But no, the network doesn't go blind. First, the controllers are always deployed in highly available redundant clusters across multiple geographic cloud regions.
So there are backups for the brain.
Multiple backups. But more importantly, if the edge devices somehow lose connection to the controller, they retain the last known good routing policy.
Oh, clever.
They keep forwarding traffic based on the last instructions they received. They just lose the ability to receive new dynamic updates until the controller reconnects.
Okay, that makes sense. So the first piece is the controller. Second, you have the service orchestrator.
The service orchestrator is the management interface. It automates configurations, provisioning, and bandwidth allocation. This is where your network administrators set the actual business policies.
So they don't have to code every single router.
Exactly. Instead of typing complex command line code into 50 different routers, they log into a graphical dashboard and set a simple rule. All Salesforce traffic gets top priority and must have less than 50 milliseconds of latency. All social media traffic gets throttled.
And the orchestrator handles the rest.
The orchestrator takes that plain English policy, translates it into code, and pushes it down to the controller.
And finally, the third component is the SD-WAN edge device. This is the actual physical or virtual box sitting in your branch, office, or data center that physically plugs into your internet connections.
Right, the boots on the ground.
It receives those compiled instructions from the controller and routes the traffic packet by packet.
Now, here is where SD-WAN completely revolutionizes bandwidth optimization and cost savings. Because the SD-WAN controller sees the real-time performance of every link, it knows exactly how much latency, jitter, or packet loss is occurring on the MPLS line versus the cheap broadband line at any given second. It can dynamically route traffic over the best performing link at that exact millisecond.
Let me use an analogy to really hammer this home. Managing a traditional WAN is like navigating a massive, sprawling city using a printed paper map.
Okay, like that.
The roads, your MPLS lines, are hardwired and static. You plan your route before you leave, and you just have to hope there's no traffic.
And if there is?
If there's a massive accident on the main highway, you are stuck sitting in a traffic jam for hours because your paper map can't tell you what's happening in real time and it can't redraw the roads.
That is a perfect visualization of traditional routing.
But SD-WAN. SD-WAN is a dynamic GPS system connected to real-time traffic data, like Waze or Google Maps. It constantly monitors every single road in the city.
So it sees the accident instantly.
Instantly. If it detects that the main highway, say, your expensive MPLS connection, is experiencing 15% packet loss due to congestion, it instantly and automatically reroutes your critical Salesforce traffic down a side street, your commodity broadband or 5G connection that is currently wide open.
Right, it just takes the detour.
And the driver, or in this case, the end user, never even knows there was a problem on the highway. The automated bandwidth allocation is entirely seamless.
And from a management perspective, it is incredibly user-friendly. SD-WAN enables customers to control and configure their own WAN using that point-and-click graphical user interface provided by the service orchestrator.
So no more waiting 90 days.
You don't need to wait 90 days for the ISP to change your routing protocol. You click a button, and the policy updates globally in seconds.
But, this brings up a massive misconception that I hear all the time from executives trying to cut costs. Because it has a slick point-and-click interface, a lot of leaders think SD-WAN eliminates the need for network engineers.
Oh, I've heard that one.
They look at it and think it's plug and play, so they can just downsize their IT department.
This raises an important question regarding operational staffing, and the answer is an emphatic no. SD-WAN absolutely does not eliminate the need for skilled WAN network engineers.
Why not?
It shifts their focus from manual configuration to strategic architecture. First of all, the physical connections, the fiber lines into the building, the 5G antennas on the roof, must still be physically procured and installed.
Right, software can't dig a trench.
Exactly.
Yeah.
Second, while the day-to-day traffic routing is automated, designing the initial architecture, defining those complex security profiles, integrating remote cloud firewalls, establishing zone-based segmentation, and interpreting the massive amount of analytics the system generates, well, that requires deep engineering expertise.
So it gives the enterprise unprecedented agility and deep visibility into performance statistics, but you still need an expert to interpret those statistics and translate business goals into secure routing policies.
Exactly.
SD-WAN empowers your engineers to be architects rather than mechanics. It doesn't replace them.
Precisely. And this leads us directly into the governance aspect. Building this incredibly complex, agile network is one thing, but maintaining its operational integrity over time is where the real management challenge lies.
So what does this all mean for the IT director or operations executive who has to actually run this beast day in and day out? This brings us to body part 4, network management and operational integrity.
To manage a WAN effectively without chaos, corporate leaders really must adopt a structured, formalized framework. In the telecommunications industry, the gold standard is the FCAPS.
FCP.
It stands for Fault, Configuration, Accounting, Performance, and Security Management. Rather than just listing these off, let's look at how they interlock during a real-world scenario.
Okay, let's say it's 2:00 p.m. on a Tuesday, and a major fiber line connecting our London and New York offices goes dark. Where does the FCPS model kick in?
It starts immediately with F-fault management. Fault management is fundamentally about detecting, isolating, and resolving network issues.
Like an alarm going off.
Right. But in a modern SD-WAN environment, it goes way beyond just setting off an alarm when a circuit fails. The primary focus of modern fault management is on resiliency and the network's ability to self-heal.
So when that London link drops, fault management isn't just a red light blinking on a dashboard. It's the system automatically failing over to a backup broadband circuit without dropping the active VoIP calls.
Exactly. That self-healing capability is the hallmark of mature fault management.
Okay, but now you have to figure out why it went down. Was it a backhoe cutting a cable, or was it a software error?
This is where we look at C configuration management. Configuration management is about maintaining a strict, auditable record of every single change made to the network software or hardware.
Because what if a junior engineer made a configuration change to the London router at 1:59 p.m., and that's what caused the outage?
Precisely. Without configuration management, you're flying blind trying to guess what broke. With a mature configuration management system, you have version control. It focuses on strip ticketing for change control.
So every change has a paper trail.
Exactly. A ticketing tool assigns a unique ID number for every configuration change, ensuring nothing happens in a vacuum. If that junior engineer's change caused the crash, configuration management allows you to instantly roll back to the last known good configuration from 1:58 p.m., restoring service in seconds.
Okay, so you've restored the network, you've rolled back the bad config, but what if the fault wasn't your engineer? What if the telecom provider simply failed to deliver the uptime they promised?
That leads us to A, accounting management.
Now, in general IT, accounting usually means asset tracking, knowing how many laptops or monitors you own. But in the context of wide area networking, that's not what this means, is it?
That's a crucial distinction. While internal asset inventory is important for general IT, it is the least useful aspect of accounting management when dealing with external WAN providers. In WAN management, accounting refers to the ongoing management of third-party vendors and telecom service providers. It is about managing vendor service level agreements, or SLAs.
So it's a financial policing of your network.
Exactly. It's conducting rigorous audits of service provider billing to ensure you are actually getting the bandwidth and the 99.99% uptime you are paying for.
Right.
If that London line goes down for 4 hours, accounting management gives you the hard data to go back to the ISP, point to the SLA contract, and demand financial credits for the breach in service.
That makes total sense. You need data to fight a billing dispute. But all the SLA credits in the world don't help if your network is technically online but running so slowly that applications time out.
Right, which brings in preset performance management. We touched on this with QoS, but it's broader than just traffic shaping, isn't it?
Yes, performance management ensures the network is operating efficiently under varying loads. This certainly involved the QoS packet prioritization we discussed earlier. But from an executive level, performance management is heavily focused on capacity planning.
Looking into the future.
Right. You must have the deep visibility required to see trending data. If you know your company is launching a massive new cloud-based ERP system next quarter, performance management tools will tell you if your current WAN links can actually handle that extra 500 megabits per second of sustained traffic.
You can't just hope for the best.
No. You cannot wait until the pipe is 100% full and users are screaming to order more bandwidth because, as we discussed, provisioning new physical lines can take months. Performance management is about ensuring spikes in network traffic or long-term growth can scale smoothly.
And finally, security management. This is the big one, and it touches every single thing we've talked about.
Tell us about BS.
Security management at the WAN level is fundamentally a business decision. It is about governance. It's where technical controls meet executive risk management.
Okay, give us an example.
The technical team will identify a vulnerability, say data traveling unencrypted over a commodity broadband link in the SD-WAN.
And the executive team has to decide how to handle that risk. Do we mitigate this risk by buying a larger set of firewalls to build IPsec tunnels? Or do we accept the risk? Or do we transfer this risk by purchasing cyber liability insurance?
Exactly. Security management must align with recognized global standards, specifically the NIST Cybersecurity Framework version 1.1, which dictates a continuous life cycle of identify, protect, detect, respond, and recover.
Right, so it's not a one-and-done setup.
No, it ensures that security isn't just a firewall you plug in, but an ongoing operational life cycle.
So when we look at the entire FCAPS framework, it's clear that these aren't just IT tasks, they are strategic business imperatives.
Completely.
The C-suite needs to care about fault resiliency because downtime costs millions of dollars an hour. They need to care about accounting management because telecom overbilling drains capital.
And that strategic understanding is what allows us to tailor these solutions to different market segments, because a one-size-fits-all approach to wide-area networking guarantees wasted capital.
Right, you have to scale.
You do not build an enterprise-grade SD-WAN for a three-person real estate office, and you absolutely cannot run a Fortune 500 supply chain on a basic cable modem.
Let's break down the exact architectural requirements for three distinct corporate scales, starting with the big leagues. Enterprise environments. What does a modern enterprise WAN actually look like physically?
For an enterprise, the WAN must be massively scalable and robust. You are typically looking at a hybrid environment. They will utilize Metro Ethernet for incredibly high-speed connectivity, often 10 to 100 gigabits between corporate buildings located within the same city.
Okay, so massive speed locally.
Right. And then they combine that with a global SD-WAN overlay to manage connections to remote global branches and major cloud providers like AWS or Azure.
And what specific technologies are they leveraging to secure these massive links across the public internet?
Enterprises heavily utilize DMVPN, or Dynamic Multipoint Virtual Private Network. This is a brilliant technology that allows branch locations to communicate directly with each other securely over the public internet.
How does that work in practice?
Well, instead of a branch in Dallas having to route all its traffic all the way back to the headquarters in New York just to talk to a branch in Austin, DNVPN builds a secure, temporary tunnel directly between Dallas and Austin and then tears it down when it's done.
It totally reduces the bottleneck at headquarters. But what about physical redundancy? I see companies mess this up constantly.
Oh, the crucial detail for an enterprise, and this is a catastrophic mistake I see frequently in audits, is employing high-speed internet pipes from two different ISPs specifically for physical redundancy.
Right. An IT director will buy a primary 10 gig link from AT&T and a backup 10 gig link from AT&T and think they are perfectly secure.
And if AT&T's core routing facility in that city goes down, or if a construction crew cuts the single trench leading into the building that holds both cables, both your links go down simultaneously.
So you have layered your security, but you have zero physical redundancy.
Exactly. You must have geographic and vendor diversity, meaning a line from provider A entering the north side of the building and a line from provider B entering the south side for true enterprise redundancy.
Excellent point. Let's step down a tier to the small to medium business, or SMB. They don't have multi-million-dollar enterprise budgets, but they still have complex, multi-departmental needs.
SMBs require scalable business-grade internet access, but their internal architecture is a bit more localized and budget-conscious. Because they aren't managing tens of thousands of global devices, they will rely heavily on NAT, or network address translation, using private IP addressing.
Let's explain NAT conceptually because we don't want to get bogged down in the specific IP subnetting math of 12 or 8 ranges.
Good idea. Think of NAT like a corporate mailroom for your data. For an SMB, you don't need to pay your ISP for a public, globally routable IP address for every single laptop, printer, and phone in the building.
That would be incredibly expensive.
It would. Instead, you use NAT. The outside world, the internet, only sees the building's one main public address. When a packet arrives, the internal router, the mailroom, sorts out which specific desk or private internal IP address the data goes to. It saves money on IP addresses and hides your internal structure from the outside world.
And internal segmentation is key for an SMB, right?
Absolutely. SMBs must utilize VLAN virtual LAN capabilities. VLAN segmentation allows them to logically separate departmental networks and traffic over the exact same physical switches.
Because the HR department's payroll data shouldn't be floating around on the same logical broadcast domain as the marketing department's graphic design files.
Exactly. If marketing gets hit with ransomware, a VLAN prevents it from easily spreading to the HR servers. They also need VLANs to establish public-facing DMZs, demilitarized zones, for their web servers, keeping those external-facing assets isolated from the sensitive internal corporate network.
And for their branch offices.
To connect their edge offices back to the central data center, they will often utilize the point-to-point protocol, or PPP, for secure, direct links.
Now, let's look at the third tier, which has become incredibly relevant and frankly a massive headache for IT managers. In the era of remote work, the small office home office, or SOHO environment.
Ah, the remote worker. The SOHO environment also uses NAT with private IP addressing to handle multiple devices on a single home internet connection. But here is the major vulnerability alert that corporate managers must understand when their employees are working from home.
Listen up, this is important.
There is an absolute necessity for VLAN capability on the remote worker's home router to logically segment the office or work LAN from the guest or family LAN.
Let's really emphasize this because this is where corporate data breaches happen today. If an executive is working from home on their corporate laptop and that laptop is on the exact same flat Wi-Fi network as their teenager's gaming console, their partner's personal tablet, and their cheap, unsecured IoT smart refrigerator, that is a massive corporate security risk.
It is a critical vulnerability. Threat actors know they can't always break into the corporate firewall directly, so they target the weak link. Exactly. If a teenager downloads malware hidden in a video game mod, or an IoT device in the home is compromised, the attacker can use that infected device to pivot and attack the corporate laptop because they are on the same logical network. They can sniff traffic or attempt lateral movement.
So segmenting the SOHO network into a strictly isolated work VLAN and a home VLAN is non-negotiable for remote enterprise employees.
Furthermore, the SOHO router must have bandwidth rate limiting and threshold setting capabilities applied to the family side of the network.
Oh, this goes right back to our QoS discussion.
Yeah.
We are doing traffic shaping in the living room.
Exactly. You must ensure that massive bandwidth, hogging like someone in the house streaming a 4K movie or a gaming console downloading a massive 100 gigabyte update, does not saturate the home internet connection and impact the corporate work happening on the other VLAN.
Priorities, right.
Yes. The corporate VPN tunnel and VoIP calls must have priority over the family streaming services.
So while the scale changes drastically from a massive enterprise to a mid-sized SMB to a remote SOHO worker, there are common denominators, right? Certain security baselines that span all three tiers.
Yes. Regardless of scale, all three tiers require strict adherence to foundational security controls. Every single environment must operate behind an IP stateful firewall, which monitors the state of active connections, ideally equipped with an intrusion detection and prevention system, or IDE-SIPS, to actively block known threats.
And what about Wi-Fi?
If they utilize wireless access, it must be secured with WPA2 Enterprise or WPA3 Enterprise. That requires individual user authentication, like a unique username and password or digital certificate, rather than a single shared Wi-Fi password that anyone can give away.
They all require web content filtering too, right? Like URL monitors to prevent users from accidentally accessing known malicious phishing sites.
Yes, absolutely.
And finally, any remote access back into the corporate network must be secured via an encrypted VPN and strictly enforced with multi-factor authentication.
It's fascinating how the foundational principles of security and packet delivery remain constant, even as the architecture scales from a single home office router up to a global SD-WAN deployment spanning continents.
Okay, let's pull all of this together. Navigating the hyper-connected marketplace today requires corporate managers to move decisively away from static, legacy circuit-switched lines. The future, and indeed the present, belongs to agile, packetized, SD-WAN orchestrated environments that are fiercely prioritized by strict quality of service protocols.
By understanding these underlying business drivers, agility, visibility, cloud migration, and by implementing these resilient edge-to-edge pathways, you ensure that the Monday morning nightmare of a dark global supply chain remains just a bad dream.
Exactly.
You're building a network that can heal itself, dynamically route around congestion, and guarantee that your most critical business applications always have the exact bandwidth they need to perform.
Thank you so much for joining us on this deep dive.
But remember, building the network is only half the battle. Maintaining its operational integrity over time is the next piece of the technical puzzle.
Very true.
In our upcoming deep dive, Chapter 12, Network Operations and Management, we will focus heavily on how that FCAPS framework is implemented in the real world on a daily basis. We will explore how Network Operations Centers, or NOCs, manage configuration change control, and how proactive anomaly monitoring guarantees ongoing operational integrity before a failure even happens. You won't want to miss it.
To ensure you always maintain that competitive edge, take a moment right now to like, subscribe, and share this deep dive. Head down to the description for direct links to our resource diagrams and technical reading.
We also highly encourage you to review our channel for other corporate IT playlists, videos, and continuous professional education modules.
Right.
If you want to expand your expertise further, be sure to check out our Digital Forensics audio series, as well as the Network Network and System Security Deep Dive series.
As you look at your own organization's infrastructure today, ask yourself a critical question. Are your legacy contracts dictating your network topology, or is your business strategy dictating your network agility? Align the strategy, optimize the network. Until next time, keep your business connected, your assets visible, and your infrastructure secure.